Welcome all to the 12th lecture of our PMRF um, NOC AE15 lecture series. This is the final session. So if today anyone joins, then well and good. But otherwise, this would be our last interaction session. And yeah, so let's get started. Okay, so let's get going. Let's get going. You remember we discussed a problem the very early, I don't remember exact session number, but the problem was this. See, now that you have been trained in thermodynamics, you would be aware for an ideal gas, V is a function of only T. In general, now that you know that every state can be represented by two independent state variables, let's say P comma T. For an ideal gas, Cp and Cv are only dependent on pressure and temperature. By convention, this is what we write. Okay. Cp as a function of P and T is a general convention, and Cv is generally written as a function of V comma T. Generally, but again, for ideal gases, both dependence on P and V kind of drops away. Now, the question was to show one, and this is two, or three. So, to show if one holds implies or one implies two or three and T, or two or three implies one. So this is a very simple problem if you think about it. Seems to be difficult. See, one part of it is easy. One way it is easy. Okay. So one way is easy. I'll tell you how. See, the CD is du by dt at a constant volume, isn't it? Whereas CT is defined as, again, I use this word. This is important actually. People can easily get confused. I will tell you. This is actually a definition. Mind that. dH by dt at a constant P. Okay. Thing. Uh, Now, if 1, then you know that H is U uh, plus PV. Now, for an ideal gas, H becomes U plus RT. So now, what does this say? This says that dH by dt uh, by dt plus RT, isn't it? Now you take you apply a constant pressure boundary condition. The pressure for a constant pressure process, what will happen? Cp will become du by dt at a constant P plus R. Isn't it? Isn't that the case? Uh, Similarly, uh, similarly, you have Cv is a function of dH by dt, which will be sorry. So this will become dH by dt from a constant V. Constant V will become Cv plus R. Now, for an ideal gas, okay, now this is something that I'm writing extra. This is not given to us. We know that H comma U are H of T comma U of T. So in that case, it is simply du by dt. Okay. Um, see. Can we show this? Pretty easily. Let's see. See, P equals to RT, isn't it? P equals to RT by V. Let me correct that. Now, this thing implies that um, by dt, there is a rule to use, there is actually a rule for this kind of thing. So what is the rule that we can actually use here? Um, Again, you might have read about this rule in the thermodynamics relation thing. The rule is dx by dy at a constant z, dy by dz at a constant x, and then dz by dx a constant y is -1. Okay. We can kind of show this also. So let me do that later on. But let me see how it applies here. So this becomes, so let's first write this identity in this term, dt by d the constant p, and then d by dp the constant p is known to us to be -1. Now you see, uh, no, something is wrong. See, du by dt, the constant p, will become dt by d p at a constant u, and this will become d p by then du at a constant t is -1. So dt by dp at a constant u will become 0. So this is 0. Wait. Let me not do this. Wait. So it is not of any help to us. Let me do this. Fine. Now, few things we know here, right? Indeed, we can actually quickly calculate also. See this relation will even help. Um, R by V times R by P by dV P by R and times, what is this? Uh, minus R by P. Yes. Now what this becomes is PRT. So R gets cancelled first of all. No, R will not get cancelled. PRT by, or even P can go away. RT by, there's the minus sign here. RT by PV, this is -1. Okay, this is one thing. Now, how do we show this thing? For an ideal gas, this is true. Let me think. Du by dt, the constant P is actually equal to du by dt, the constant V. So generally, RT. Now, du by dt, the constant P plus similar thing slightly changed. Yeah. So now you know this is unity, okay? This one is unity. Um, for an ideal gas, what all do we know? Um, Actually, this is the correct term. Okay, I did not. This is not exact. Important that these partials are used rather than totals. Okay, so now we realize that this is CV. Okay, CV. Give me a second. Now del U by del V at a constant T for an ideal gas is zero. We realize that because U is only a function of T for an ideal gas. U is only a function of T, and then it will imply that this term is zero. So you see that du by dt at a constant P is CV. That is one thing. Similarly, you can also show this part that del H dH by dt at a constant V is P. This should be Cp. Quickly we can show. It's like how we showed it for du by dt. You can show it for dH by dt. Okay. So now uh, essentially now what does CV and CP uh, for an ideal gas? See, for an ideal gas, what does it mean? It means that for an ideal gas, so why is this zero? If CP is a function of or CV is a function of only temperature, how do I imply this? Okay. For an ideal gas, first of all, let's realize that du will be this term is like now this now for an ideal gas, we just quickly saw that um, Okay, so do I need to show here that this thing is zero? How do I show this? Okay, this is doable. So now we will use real gas thermodynamic properties. Okay, and how essentially are we going to use it? Let's see. So let's use first TDS relations. Then let's just add. No, there are four Maxwell's relations, right? Let's add or subtract. Um, we'll add and subtract this thing. S dt minus S dt. Yes. So now this term gets combined to be d of Ts, which can become H minus Ts, and then even simply even here we'll repeat the process to say that we'll add plus S dt minus S dt so that you get now this H minus Ts, U minus Ts are roughly two energies, right? One is gives free energy, one is Helmholtz free energy. Don't right now ask me which one is which. I just know that one of them is, think Helmholtz is H minus Ts, gives us U minus Ts, right? Yeah. So now we have four Maxwell's relation. And what is the Maxwell's relations here that we are going to derive? We are going to say that because this is the exact relationship. See this. Let's look at this one. Um, if I represent, if I represent H as a function of H S comma P, then essentially I will have dH equals to TdS. Oh, wait, it will be partial H PP, and then similarly you will add this thing here. This becomes ds, this becomes s, and it becomes p. Okay. Now, one thing to just quickly write here is that is T and is V, right? By just comparing these two equations. But at the same time, you must realize um, basically what I'm trying to write here is then when we say that dm is a function of n dx plus l dy, do we not write this thing there? And where is this coming from? This is coming from exactness of this relation, that over a closed path, these should not these will become equal, right? These should become equal. I think this is done in your lectures. Okay. Here is, and mind that in this relation, this is the condition. One way to see this is, let's take yes. So it should be equal to, isn't it? This is something that we know, right? That's the definition of n and n, just substituting things. So that in that sense, you can actually write this. Um, so now this is something that I need to write, is equal to. So this is the first or second Maxwell relation, depending, like it's one of the Maxwell relations. Let's put it this way, at a constant t. We can write three more of these. So let me do that. That to derive the ideal gas thing. Why only with the, so the idea is that this thing, or U is only a function of temperature, or internal energy is only a function of temperature, only works for this particular equation of state. It cannot work otherwise. If it has to be this RT, cannot be RT square or RT to the power 1.3 or something. It has to be exactly RT. Only then U is only a function of temperature. It won't, otherwise it won't work. So let's look at it. But before that, let's try to see that if CV is a function of T, can be kind, or if for an ideal gas, can we show that del U by del V at a constant T is zero. So before that, so this is the progression. But let's forget about the progression for time being and let's just derive the other three Maxwell's relation. So the other one, the first one is actually del. This is V, the constant S. This is minus P, the constant V, right? And the other one is P at a constant T with a minus sign. Uh, this will be T comma. This is the fourth Maxwell relation. Mind, this is a Maxwell relation with thermodynamics, okay? And then the fourth one is uh, P at a constant T at a constant V is del S by del at a constant T. Okay, and this one I've incorrectly written it to you. Now with this, let's try to write the general U. If I had to write U as a function of V comma T, I would write this. Now this is known to us as to be CVDT. It is kind of known to us. So this is the non-ideal part. That whatever we are seeing, this other thing. Um, and then similarly for DH, as I told you, by convention we use it as a function of temperature and pressure. So now let's try to find out what is this. Okay. Uh, mm, we will use TDS relation. Right? The TDS is actually minus P by T dV. Isn't it right? Let me check. Yeah, it's all correct. Yes. Now, using a similar logic, Just let me think. I can use. Okay, yeah, wait. I have few things. Why have anything to use here? Maybe I think I have. Let's say S is a function of T comma V. Then df is one of the factors related with see. You see this in commentaries, right? Okay. So now the trick is to substitute this in this expression. That is the great trick. Right this and take this PV constant on this thing, a common quantity. Yes. Now this will become this relation with this equation. We realize that Cv by T is ds by dt at a constant V. And then del U by del D at a constant T is actually this term. And that is what we can use to quickly show on this side will Q. And in fact, now that I told you, you could actually use this as well. Now no. For a function of T. That is like an intermediate step that you will have to follow. This term should be zero. Now, for an given an ideal case, you can quickly calculate that this will be exactly. This will go to zero. But what if this is the case, and you need to prove that P by T equals to R, PV by R is 1. For that purpose, the equation that we get is this. Okay. And then a similar logic will also give you I can show later. Okay, now let's just quickly see what are we doing there. Is that okay? Now see what you are getting. You will get dt by t is dv by v plus dp by t. You will also get that dt by t will be t dv by dv. This is the thing. And now if you take if you integrate this, you basically get E equals to K times PV. Let me put it like this. PV equals to KT. This is the important thing. So first of all, for u to be only a function of t, T equals to KT is required. Now, once you have proven that u has to be a function of t, then you can kind of derive and show that q is only a CV is only a function of t. How do you do that? We go back. We see that if q is only a function of t and it does not depend on v, then this goes to 0. Uh, and then because u is a function of only t, CV becomes to be, by definition, has to be only a function of t and o, right? Function in t, the derivative of function on t will at max depend on that variable or temperature, right? It cannot depend on anything else. It cannot because u is not dependent on p and v separately, independently, and so its derivative with temperature should also behave like that. So that's how you show CV and CP are also functions of only t. Okay. Now I use the expression here. How do you derive this? What you do is you whatever I did for du, you do it for dh to get this. Let me see if we can do that now. Okay, let me show that to you. dh that no is that correct? I think this is fine, right? Now, one thing you know here, this is CP, mind. Now, next thing, we need to calculate this. Okay. For this, I go to the relation that df d d at a common p this this. Now, again, Maxwell's relation have to be used, but let's not use it right now. And also write dds is equals to dh minus vdp. Now, if I do this, then essentially what am I getting? dh is vdp plus this entire thing. Okay, now you take this one. Again, now comparing, you have to compare it with this relation. If you compare, you find out that del H by del P at a constant T have to be equal to this. Then you substitute this relationship. Now, if you do that and use the Maxwell's relation, you get a minus sign here. Uh, the GDP comes out. So, and the issue is it was multiplied by t. Find that. That's it. Then by del t, constant t is big. Only for an ideal gas with PV as a linear function of t, can we have u as only a function of t and h as a function of t? That is one exercise that I had indicated early on and showed it today in the last session. Okay, let's move on. Okay. Well, now next 10 minutes, 5 10 minutes, let's take a break and then I'll come back. Okay, let me take a 5 10 minutes break and I'll come back. Okay, so let's start solving problems, and I'll try to do them. Okay. Listing things. Consider a rigid tank that contains a mixture of two ideal gases. A wall is opened and some gas leaks. As a result, the pressure in the tank drops. The partial pressure and pressure fraction of each component will, your options are remain the same and decrease rapidly, uh, remain the same, both of them will remain the same, or decrease, remain the same rapidly, decrease, comma, decrease. Effective. Okay, now let's try to answer this. What does the question boil down to? It is essentially asking that if we lose the amount of mixture, what essentially happens? Does the partial pressure and pressure fraction of each component remain the same or what? See, definitely if you have a closed rigid tank, you're dropping the pressure, then your partial pressure is going to decrease. So at least we are clear about that. Now, what about pressure fraction? Now, because the composition of the two ideal gases will not be varying, so that will remain the same. The next question is, how will the specific humidity and the relative humidity of the air contained in a wall filled room as it is heated? So your options are specific humidity will increase and Raj, let's put it like this. Let's put blanks. What will happen to specific humidity? What will happen to relative? I think the question is essentially what happens to temperature. Does specific humidity will get increase or decrease? It should remain the same. Why? Because it is actually good. It's a mass fraction of paper per unit mass of air. Right? Specific humidity remains the same. That's what about relative humidity? See, when increasing temperature, the saturation pressure increases. So the maximum amount of air that air can hold increases. So relative humidity must increase. That's the solution to this question. Um, Third question is a substance whose Joule Thomson coefficient is negative, is throttled to a lower pressure. Pick the correct option from the following first process. Your options are your options are temperature will increase, rate increase, decrease, and then two options. The other two options are entropy remains constant or decreases. See, if the Joule-Thomson coefficient is a negative term, then at a constant enthalpy, dT by dP is negative. Now, because dT is just negative, temperature should increase, and that's the correct option. Okay, increase. Because it's a throttling process, entropy cannot decrease; it has to increase because we are kind of assuming that there is no heat transfer. And if there's a heat transfer, then this is not an isentropic process. It's not a purely throttled process because then dH will not be constant. Um, and in that case, if it's adiabatic, dH by dt, so dt by dP will be so there will be ds, and that ds will be entropy generation. There will be generation of entropy due to irreversibilities. Uh, yeah. Now, yeah. Now the question from thermodynamic relations for a gas with E minus B goes to RT, we need to tell what is CT minus C. What is CT minus C? Okay. I think whatever we did just now might be useful here. Uh, okay. This is definitely not an ideal guess. So you are going to use two equations. Whereas So here we can actually put at a constant V. So plus PV minus BP, PV is RT. At a constant V, what is dP by dt? In essentially R by V minus T. Which is this still becomes low. U will be H. Here, the constant dV by dt is RT by V, right? Yeah. But this is not zero, right? This is not zero. Can use an relation that Cp minus Cv is equals to minus T partial T by constant. Need to substitute things to figure this out. We don't expect, like, nobody would expect you to know this. Remember this expression, it is kind of will be given to you. Now, given that you have open book assignments in NPTEL and all that, that's why such question exists, because it is kind of expected that you are going to refer to the books. In that case, let's just substitute few things. What are we getting here? Minus T times R by V minus B whole raised to power square divided by, okay, RT there will be a minus here, I think. Wait a second. P, a constant P. Yeah, that's all right. This will be V minus V square. Now that will simply become, wait, there will be a minus sign, mind that, and then this will become simply R. So note that in this case, although Cp minus Cv is R, it's not that H is only a function of, H is not Cp dt here. There is a term. So RT by T is actually V minus B, okay? So this will be actually BD, mind that. Just to show that this is not an ideal gas, okay? Okay, although Cp minus Cv is R, it's not that it's an ideal gas. Just mind that. Yeah, I think at this point, I think more or less all questions are easy. It's not the questions that are hard. We can review what have you been doing throughout different lectures. Okay, so let's start that. So I started with a small overview of what open systems are, closed systems are. How our state point, how the three laws are very similar to definitions. They are actually definitions. Actually, don't talk about the third law because it's a statistical thermodynamics law, not much thermodynamics or classical thermodynamics there. Then we slightly talked about the exact differential and the uh, yeah, path functions and the point functions. Some questions, very questions on nanometer. This is both elements. The second part, I think we continued that discussion. Simple questions, simple questions. Yeah, and then came this Gibbs phase rule, and then pure phase, pure substances relations came. So we discussed slightly the number of a simple compressible systems definition, how different force interactions increases the number of state points of your system. Um, Again, not very specific questions. Then we discussed one day about saturation temperature, critical point, and amongst other things. Um, we also discussed compressibility effects, van der Waals equation, did some steam table questions. Those are straightforward questions. Yeah, you can also explore that. And then we discussed in one class we discussed how ideal gas equation and van der Waals equation was a simple yet powerful addition over gas equation. Different gas laws, how ideal equations came picture, and then van der Waals equation was a simple addition. Discuss two experiment. Exact thing we are solving about. So this thing that we discussed in the first classes. Then I also discussed how I guess equations are like suggesting quantity isotherms, whereas the when Wonder Woman kind of started getting a solution to what are new solutions, so we started getting features of actual isotherms, real isotherms, and Yeah, then use this sample to solve for the critical temperature, critical pressure, energy. Uh, what is the actual definition of energy? Is it CV by dU by dt at a constant or all those things? Um, discuss what is the ideal gas, what is the theoretically perfect gas, what is the, yeah, so those kind of things. And I also discussed if we can actually consider CV as a function of temperature alone. What does that require? Right? Certain amount of questions then came when we started discussing first laws for closed and open systems. So this is for open systems. Energy equation for an open system. Certain problem there. Entropy now started coming to picture. Then we again started solving some questions on the steam tables. Then we discussed the second of thermodynamics and heat engines, questions around that, efficiency questions. Then I also discussed with you thermodynamic temperature scale and how the Kelvin scale is a linear scale in like it kind of Kelvin scale kind of is a definition. Uh, see, this thing is by definition. Okay, just mind that. These are by definitions there. Why in hell will heat transfer rates be equal or proportional to the temperature ratios or temperatures? It's by construction. It is by construction. We have constructed temperatures to be of that sort. So we are kind of creating a scale that scales with the heat transfers. And then I told you about TDS relations and how it is an identity, not for specific processes. Yeah, we discussed for we also discussed Clausius inequality, entropy questions. We did few questions on entropy. Largely, first simple multi-choice objective type questions. This is something that we did recently on a reheating problem. Then this is for a, I think, uh, for a steam regenerator, something that we did in the last class. Again, this is a confusing thing which we did say in the last time. What is the work done in a closed system? Is it DDP? Is it PDP? What is it? So that is also important. We discussed that part, and then we discussed few more questions. Uh, Auto cycles. And yeah, at that point, this was kind of our last class. I think, yeah, more or less we are set. I don't think there is very complexity in the air conditioning chapter, gas vapor mixture thing, and psychometry essentially. I think that is a good point to stop. And I wish you all the best for your exam, and hope to meet you at some point of time in time. So yeah, all the best, guys. Sadly, today nobody joined, which is also understandable because your exams are now closer. So these sessions are little less helpful. It is better to prepare rather than attend these sessions. So anyways, it was nice connecting with you guys, and hope to see you, meet you someday. And all the best for the class. Thank you. Logging off.